Hello, this is the last lecture in our fluids unit on Bernoulli's principle, and the essential question is, how is energy conserved in a fluid system? So we've already talked about what conservation of mass looks like in the continuity principle, but seeing energy in a fluid is a little bit trickier. Since fluids aren't held together by those tight bonds that solids experience, different parts of the fluid might have different types of energy at a given moment. In a solid, right, if you know the kinetic energy of one part of the solid, you know the kinetic energy of the whole thing because it's moving together. Same thing with potential energy. It's at the same location, give or take, in space, and so the potential and kinetic energy of a solid are pretty self-explanatory. However, on fluids, because they're not actually, when you move one part of the fluid, the other part doesn't have to move. You can't really see energy the same way you do in solids. However, the conservation of energy is still going to apply within a fluid system, which basically means that the energy, or if you will, the energy per piece of that fluid. So throughout the system, every little piece of fluid has the same amount of energy, even if that is different kinds of energy in different parts of the fluid. And from this sort of basic core principle, we can do a kind of interesting derivation that's going to help us come up with a tool that's really going to be a powerful one. So if we know that energy per volume is sort of the conserved property in fluids, and we do a little unit analysis, energy is a joule and volume is meters cubed. A joule can also be described as a Newton meter, right? If you know work energy theorem, force times the distance per meter cubed. And then we can actually cancel out one of those meters, and we end up with Newton per meter squared as being the same fundamentally as a joule per meter cubed. And then if you think back to our very first lecture where we defined our new variables, you may remember that a Newton per meter squared is the same as a Pascal. So why do we care about this? Well, if a Pascal is the same as energy per volume, that means that in fluids, energy is actually stored in pressure. So pressure becomes this new thing that can be conserved in a fluid. Bernoulli's principle, which is the topic of this lecture, says that the total energy stored as pressure is the same at every location within a fluid system. So even though we might have different kinds of energy, the total amount of energy stored as pressure is the same at this location and this location and this location in my complex fluid system. So you've already heard me reference a handful of different kinds of energy. So there's actually 3 different types of energy that we can store in pressure in fluids. And the first one is actually the one we're familiar with already. It's the mechanical pressure stored up in the fluid, which is represented by a capital P in equations. This is the energy stored that's in the chemical bonds between the molecules, and it's essentially can be represented by the pressure that fluid is pushing out on the walls of the container, or the pressure that's pushing in on objects that are inside of the fluid. When you know the value of this mechanical pressure, you can apply our original pressure equation to this kind of pressure specifically to find the mechanical force acting on like a portion of the wall of a container, for example. One sort of real world application here, I don't know if you've ever seen Bug Out Bob. We have 2 different Bug Out Bob systems, one in the top and one in the bottom. And inside the system of Bug Out Bob, in each system, we have to have energy being conserved. And the top, we have a system that doesn't have as much energy per volume, and therefore is not exerting nearly as much mechanical pressure on his face. It's a little bit of pressure, and those walls aren't being pushed out very hard. In the bottom, I have a different system, a different fluid system that has a higher overall energy per volume because we've added some energy by squeezing. And that means that the mechanical energy stored up in that fluid is higher, and it's pushing out harder on the walls, and it's making Bug Out Bob's eyes bug out. So the second kind of energy that you can find in areas in fluid systems is gravitational energy. And we're already familiar with gravitational energy from our review at the beginning of the year, but gravitational energy is energy that is stored up in the gravitational fields of objects as you pull them apart. So as you pull something away from the center of Earth, you store up energy in this gravitational field. Of course, in fluids, we're not going to use quite the same equation that we use for regular solid objects, and that's because we care about the gravitational energy stored per volume instead of the overall gravitational energy of the fluid. So if we start from that starting place, UG over volume, then we can do a quick little derivation. Gravitational energy, of course, is m times g times y, where y represents the height of the object, divided by the volume of the fluid. And mass over volume, this little portion right here, is the same as density, right? So we can replace that m over v portion with density, and we end up with this new equation, rho g y, which represents the energy gained by lifting fluids away from the surface of Earth per volume of the fluid. Wow, that was a lot. And I know this whole slideshow is kind of a lot, so let's just go through it a few times and you guys will get a lot of practice applying it in a little bit. A quick note about this, as I already sort of mentioned, but the y in this equation is the height of the fluid measured up from the bottom of the container. And the reason why this is a common error is because this equation is exactly the same as hydrostatic pressure as measured down from the top, except it's a y instead of an h. So you got to be really careful realizing that we're measuring from different perspectives. What it boils down to is the higher the location in the fluid system, the more gravitational energy that little chunk of fluid contains per volume. So if you think about this fluid system here represented by these fountains, the top of the fountain, the water has a lot of that rho g y. We've got a large y as measured up from the bottom. And water that is near the bottom of the system, so the water that's at these really low little fountains, that per volume has a lot less rho g y. So eventually you're going to discover that if this water has a lot less rho g y, it better have a lot more of something else, because we're all part of one system and we've got to have the same amount of energy at every location in the system, even though that energy might be changing types. So the third and final type of energy stored up in fluid systems is actually our old friend kinetic energy, but it's going to be the fluid form of kinetic energy, which is kinetic energy per volume. So it's the kinetic energy of a little piece of the fluid, not of the entire fluid system. So kinetic energy of anything is going to be the energy contained by a moving object, in this case a moving fluid. If you've ever been squirted by a hose, you know that that moving fluid contains some energy. We can do the same derivation we did with the gravitational energy per volume. We start with kinetic energy per volume. We replace that kinetic energy with the equation for mechanical kinetic energy, which is 1/2 mv squared over volume. And I actually did the exact same thing with the mass over volume here. I'm going to replace that with density, and I get this equation right here, which is that the energy stored in a moving fluid per volume is 1/2 rho v squared, which looks a lot like the mechanical one, but we've got that density in there. What this sort of means in terms of relationships is that the faster the fluid is moving, the more kinetic energy that little chunk of fluid contains per volume, right? So the fluid that is moving fast is going to have a lot more kinetic energy down here, and the fluid, like in the top of this bucket, that might be going down but very slowly, is going to have a very small amount of kinetic energy at that location in the bucket. One little reminder, this equation is often used together with the continuity equation, because when we're in a fluid system with pipes, for example, the volume or the velocity depends on the area. So often you're expected to calculate the V that you will be using in this equation by first using the continuity equation and the area of the pipe. Okay, so each of those hopefully felt manageable or comprehensible, or you understood the relationships that went into them. It's only when they get combined together that this becomes the ugliest equation on your equation sheet. And the good news is we're getting to it early in the year. So once we've tackled this equation, all the other equations for the rest of the year look a little bit more straightforward. Bernoulli's equation basically says that the total energy per unit volume is the same at every location in a fluid system, but that there's 3 different kinds of energy that might exist at any location. So the top of that equation is basically location 1. And what we want to do is you want to sum up the mechanical pressure, the gravitational energy pressure, and then the kinetic energy pressure at location 1. And whatever number you get when you add up all three of those energies has to be the same as when you add up all three of those energies at any other location in space. So those three energies summed is always the same as the sum of the same three things at a different location in the fluid, at any different location in the fluid, as long as we have our continuous fluid system. So we're going to go through one sample problem. And the good news, which you'll discover next time we meet in class, is that AP almost never gives you a problem at all anywhere close to this complex. They usually find a way to cancel out several of those terms so that the equation becomes much more simple. And you'll see that in your practice work as well. But let's go through one that's more complex so that when you see the easier ones, they feel really easy to you. For example, we have a fluid system of a pipe that is changing diameters and also changing heights. We're starting off at low and big, and we're going to go, narrow down and get higher. And I am going to do a Bernoullis problem that involves 3 different locations in this pipe just to make it really complicated. Number 1, which is down there in the wide part. Number 2, which is kind of in the middle where it's narrowing down. And then number 3 is actually outside of the pipe, but the water's squirting out the pipe, and it's still continuously connected, so it's going to be part of the system as well. So what I would probably do is I would set up a table where I have all 3 locations and 4 different columns. Column 1 is for the mechanical pressure, column 2 is for the gravitational energy stored as pressure, column 3 is for kinetic energy stored as pressure, and then I'm going to put a total column because that's where we're going to see this conservation of energy come up in this equation. And I would probably do the gravitational energy first. Gravitational energy is pretty straightforward because the only tool that you need to measure it is a meter stick. And in general, if you can measure the height change of that fluid, it's pretty straightforward to calculate. Gravitational energy increases with height from the bottom, and the 0 gravitational energy actually really should be at the center of Earth, but that makes life complicated. So you can actually define your 0 gravitational energy anywhere you want. Usually physicists define that at the bottom of whatever system that we are interested in, so the lowest location. So what I would probably do is I would say, let's assume our gravitational energy is 0 at location 1, because that's my smallest location. Then, assuming I know what the fluid is, all I have to do is measure the height in meters of location 2 and location 3, and then do some quick algebra to do the density of the fluid times 10 times that height. And let's say I got some values at location 2 of 10 pascals and 20 pascals for location 3. Next thing I would do is I would tackle the kinetic energy per volume. Now, kinetic energy, remember, increases quadratically with velocity. It's a 1/2 density v squared. I already know the density. It's the same as it was in the gravitational energy equation, so that's easy. The hard part is finding the velocity. And remember, it's a v squared unit. So as your velocity goes up, you're getting quadratically more kinetic energy. Now, there's a couple ways you could find the velocity of this fluid. You could have a little barometer in there inside your fluid tank and measure how fast that velocity is. That's a complicated piece of mechanics. Usually what people do instead is they just measure the diameter of the tube and they use their continuity equation to figure out what the velocity is. You could measure velocity somewhere when it's coming out or going in, but it's really complicated to try to measure velocity in the middle of a fluid system because you don't want to break your pipe to do that. So in any case, this is where you would usually use the diameter of the pipe with continuity to find velocity, and then you can go through eventually and calculate that term. So what we can say, though, just qualitatively, is as the pipe narrows, we know the velocity of the fluid is going to go up. So I'm expecting that to go up. Let's say I already did the math voodoo for you and calculated that the kinetic energy stored as pressure at location 1, based on its velocity, the pipe diameter, whatever it is, was 5. So I'm not doing all the work of every part of this. I'm skipping the steps to the end game where I found it, 5. And I know that velocity is going to be speeding up. So let's say we find that the kinetic energy at location 2 is 45, and the kinetic energy at location 3 is 80. Oh, I should have said this is all in kilopascals, just to make our lives easy at the end. So I put in those values based on the continuity equation that I calculated. The third part is the mechanical pressure, the third term. Now, reminder that the walls exert or experience this much force on or from the fluid. So I'm really looking for how hard is the fluid pushing on the wall at location 1, how hard is it pushing on the wall at location 2, and how hard is it pushing on the wall at location 3. Well, that's actually a really tricky thing to measure by and large. Without a force plate or something embedded in the wall of the pipe, it's hard to know how hard things are pushing out until they burst your pipe, and then you know all too well how hard it was pushing. But the cool thing about location 3 is it's not actually in a pipe. So I don't have to measure anything. I know exactly how hard the water is pushing out at location 3 because it's in the atmosphere. It's being squirted out of the pipe. It's pushing against the atmosphere and the atmosphere is pushing against it. And that means that the mechanical pressure at any spot outside of a tube is always going to be exactly 101 kilopascals on Earth. It's atmospheric pressure. So I can actually put in right now that the pressure at location 3 is 101 kPa because it's not in the pipe. This is one of the reasons why when you're doing these systems, you often want to choose one location that's either on the surface of water, like open, like a tank of water that's on the surface, or in a stream of water that's being squirted out of the pipe because you know the mechanical pressure at that location is always atmospheric. At this point, we're going to actually start applying our Bernoulli's law. And what we know is that Bernoulli's law basically says that the sum of all three of these energy types is constant at every location in the pipe. So at location 3, I have all three values. I can add them together and I get 201 kilopascals. So now I know that everywhere in the system, the fluid has to have 201 kilopascals of energy stored at some kind of pressure. Different kinds, but 201 total. So that means that at location 2, we're going to have 201 kPa. At location 1, we're going to have 201 kPa. And now we can finally fill in the rest of our table because we can calculate what had to be the mechanical pressure at location 1 and location 2 to make those sums total. And that is the really most useful piece of information we can come up with, because now we can predict things like, is my pipe going to burst at location 1 or 2? Where is the pressure highest? Where are we most likely to have problems in our system? So I know that was complex. Hopefully you followed me through it and paused if I talk too fast, and we'll do a lot more work with this later on. Thanks. Okay, we made it through the derivation of the most complex equation of the year, and the essential question for this is, how is energy conserved in a fluid system? And hopefully you can answer that conceptually and also a little bit mathematically. We haven't talked a lot about why we care about this, but it turns out there's lots of reasons why we care, including being able to fly an airplane. So we'll be doing some fun demos and some conceptual work with this later on. Thanks for watching.